This is content of part 9a if you are interested only in specific part of this video. Just jump to its start time. Next, I will talk about an experiment which is called the second harmonic measurement of the damp-like torque and field-like torque. Incorrect interpretation of this indirect measurement has made some confusion in the field for a while. Now, this indirect measurement can be explained and understood based on direct and high-precision method which I have just described in this set of videos. I hope the lesson will be learned that a critical view should always exist on a free interpretation of indirect measurement, and independent proof or direct measurement should be always used before any final conclusion. In this experiment, the current is modulated at low frequency and the second harmonic of the Hall voltage is measured by a lock-in amplifier. Since the Hall voltage is linearly proportional to a product of the current and the perpendicular component of magnetization, the beating between oscillation of current and the oscillation of magnetization generates a second harmonic. It is important to emphasize that the second harmonic measures the current-induced modulation of perpendicular component of magnetization, which are of the same frequency and in phase with current modulation. Otherwise, there would be no frequency beating. It is also very important that the magnetization modulation is very small. It is the reason why the lock-in technique is used. The change of magnetization usually does not exceed 0.1%. So there is a question whether the measured quantity which someone can name the torque can reverse the magnetization. The answer is no. The magnetization change is so small and cannot lead to the magnetization reversal, except when the condition of parametric magnetization reversal are met. As I explained previously, a very tiny modulation of magnetization direction may be enhanced in resonance, which may lead to the magnetization reversal. Of course, in order for the magnetization reversal to occur, all required conditions for parametric resonance should be met. Firstly, there should be magnetoresistance of any type, GMR, TMR, AMR, and so on. Also, other conditions of parametric resonance should be met. Next, I will explain why the second harmonic is an indirect measurement. As you can see from this formula, the amplitude of second harmonic is linearly proportional to the magnetization change. Therefore, this measurement is a very direct measurement of the change of perpendicular component of magnetization. However, this measurement cannot identify what causes this change, what is the sources of this change, and what is a contribution from different sources. So what are the sources for change of perpendicular component of the magnetization? The first source is magnetization precession. If the magnetization can be reversed at a larger current, there is a magnetization precession at smaller current. It is a very fundamental property of the spin. The perpendicular component of magnetization is proportional to precession angle. The larger precession angle, the smaller perpendicular component of the magnetization. Such a change of the perpendicular component of the magnetization due to the magnetization precession can be measured with a high precision by this method number 1, about which I will make another video and explain all details. The second source is a magnetic field induced by spin accumulation or offset field, shown here, this field can be measured with high precision by a measurement method which I have described in this set of videos. It has two in-plane components, along current and perpendicularly to current. The in-plane field shows here by red arrow. The in-plane field tilts the magnetization and therefore reduces its perpendicular component. The third contribution is the current modulation of anisotropy field. In equilibrium, when the magnetization is perpendicular to the plane, the change of anisotropy does not affect the magnetization angle. However, when there is additional external in-plane magnetic field which tilts the magnetization, the modulation of anisotropy field modulates the tilting angle. As you can see, the anisotropy field is clearly modulated, and modulation is not so small. That is this function of perpendicular magnetic field, and it's as function of the current at one fixed perpendicular magnetic field. And the fourth contribution is planar Hall effect. It means that these three contributions contribute not only through the anomalous Hall effect, but also through planar Hall effect. The planar Hall effect is second-order magnetotransport effect. It means that the Hall voltage of the planar Hall effect is proportional to vector product of the magnetization and the magnetization. As you can see that the current modulation modulate all these three components and this vector product for the Hall voltage. Therefore, one might expect that the Hall voltage of planar Hall effect should be proportional to the third harmonic, but not the second harmonic. It's not always true. If we take a deeper look into details, we can see that, in fact, the planar Hall effect is proportional to product of perpendicular and in-plane component of magnetization. The perpendicular and in-plane component of magnetization are related through his Pythagorean relation. If current modulates in-plane component of magnetization, perpendicular component has a zero and second harmonic components because of this Pythagorean relation. As a result, the contribution of planar Hall effects give a contribution to second harmonic but not to the third harmonic. The situation becomes more complex when the magnetization is tilted by external in-plane magnetic field. You don't need to follow all these details. I only want to emphasize the complexity of correct interpretation of second harmonic measurement. As you can see, the voltage of the second harmonic has a large number of different contributions. It's truly a complex mixture of many factors. Each contribution has its own dependence on the in-plane and out-plane external magnetic field, on the nanomagnet parameters such as the anisotropy field and the coefficient of spin-orbit interactions. It's really challenging to extract reliable information from this measurement alone. That is the reason why there are many contradicting publications on this topic. When a sample is changed or measurement conditions are slightly changed, one can get a very different and unexpected result. I feel some researchers use such a good opportunity to publish a large number of papers just to increase their scientific indexes. Having said that, I must emphasize that many researchers have tried hard to solve all puzzles of this measurement. However, the second harmonic is just an indirect measurement which does not contain all required information to explain its own data. The explanation simply requires more data and more independent measurements. A direct measurement is a key to clarify all puzzles. The puzzles of second harmonic measurement created many science fiction stories and unjustified suggestions. One such suggestion was that it is possible to measure individually the damp-like torque and field-like torque, just by measurement of second harmonic. For this purpose, the second harmonic is measured for scan-off in plane magnetic field along current and perpendicular to current. Each measurement was assigned to a different type of torque. The suggestion was based on the correspondence of observed symmetry of measured data to the symmetry of these two types of torque for magnetization reversal. As you can see, damp-like torque does not change polarity when the magnetization is reversed. In contrast, the field-like torque changes its polarity. The suggestion sounds reasonable. Now, having the direct measurement in hands, we can examine whether the suggestion was correct or not, and whether it is possible to associate the above described experimental measurements with these classical torques. So next, let's take a look at measured data. For example, let's take a look at data of this nanomagnet. It's very average nanomagnet. There's nothing particular about this nanomagnet. The first parameter which is changing by the current is the anisotropy field. This graph shows the measured anisotropy field versus perpendicular to plane external magnetic field. Lines of different color correspond to a measurement and different current. Here, the same graph, but anisotropy field is plotted versus current density. Here, the current density at fixed external magnetic field shown here. You can change. The upper graphs show the derivation of anisotropic field with respect to current. These two graphs, or two sides, show the same measurement of anisotropy field for different scan direction. The left graph is for scan when the scan in plane magnetic field is directed along the current, and the right graph shows the measurement when it is directed perpendicular to the current. The measurement for two scans are identical, which is expected. It is because the anisotropy field is scalar but not vector, and therefore does not have any components along different directions. It is in contrast with offset field, which is a vector, and therefore the plane component of offset field, as you can see here, along and perpendicular current are different. Another fact to notice is that there is no step-like change of anisotropy field and small external magnetic field. A small external magnetic field, the magnetization is reversed. It means that anisotropy field is independent of the magnetization polarity. It is well expected again because the anisotropy field is scalar. Again, it is in contrast with offset magnetic field, which has a step change at small external magnetic field due to its dependence on magnetization direction. The current modulation of the anisotropy field cannot be associated with either of these two torques. The anisotropy field is a scalar parameter of nanomagnet. It is very ridiculous to suggest that the change of anisotropy can be originated or created by any type of torque. Current modulation of anisotropy field can be used for the magnetization reversal, but not because of any type of torque, but due to the parametric mechanism of magnetization reversal. The second parameter, which is modulated by current, is the magnetic field which is created by spin accumulation, or offset field in short. This graph shows the measured offset field as function of external magnetic field. Lines of different color correspond to measurement at different current. Here's the same graph, but offset field is plotted versus current density at fixed external magnetic field, shown here. The upper graph shows the derivation of offset field with respect to current. It looks like the offset magnetic field has symmetry features similar to that measured by a second harmonic, and therefore can be associated with one of these two torques. It is important to clarify this because these two torques of different symmetry are introduced mainly because of measured symmetry of second harmonic. As you may recall, we have measured offset field from magnetization tilting angle. Perhaps it is possible to explain the measured magnetization tilt by a torque instead of offset magnetic field. For example, initially the magnetization may be tilted by one of these torques to some angle, at which the opposite torque, for example the conventional damping torque, increases and balances back these torques, resulting in a tilt of magnetization which is measured. It makes no sense from the quantum mechanical view, because from this view any torque-like process leads to magnetization precession, but not to a tilt of magnetization. However, from point of view of classical mechanics, such a story of two balanced torques is possible. For a moment, let us assume such a story is true and check how the measurements support this story. It helps to understand the reasons behind the misinterpretation of second harmonic measurement. In this misinterpretation, the specific torque is associated with symmetry of measured second harmonic with respect to magnetization reversal. The damp-like torque is independent of magnetization reversal. The field-like torque is reversed when magnetization is reversed. If we look at this data, the data looks asymmetric with respect to magnetization reversal. As a result, the torque should be linearly proportional to magnetization and therefore should be associated with the field-like torque. In contrast, for the opposite scan, the data looks symmetric with respect to magnetization reversal, at least in zero approximation. Therefore, the data needs to be associated with a damp-like torque, which is proportional to m squared, so symmetric. Because of different symmetry, these two data of opposite scans seems to be a result of two different torques or two effects of different symmetry. It is not correct. These two data as a result of one effect of one subject, the magnetic field H offset, but it is a vector-type object which has both magnitude and the direction. You can see it more clearly if we plot two measured components, this one and this one, against each other in one plot here. Just push here. The x-axis is component of offset field along current. The y-axis is the component of offset field perpendicular to the current. Lines of different color correspond to measurement at different current. Each point corresponds a measurement at different external magnetic field. You can also plot the data for only one fixed current, shown here, current density. You can see in this graph a clear behavior of one vector subject when external magnetic field is changed at different points, the magnitude and the direction of this subject are changing. Also, the direction of this vector subject is reversed, where the external magnetic field is reversed, but it's not fully symmetrical reversal. Yeah, you can see for different currents. To conclude, even so, the direct measurement shows a similar symmetry feature as a second harmonic measurement, at least for the measured offset field. It looks like it is an unjustified suggestion that the two different subjects, for example, two different types of the torque, are responsible for such different measured symmetry features. It looks like two scans measured just two components of one subject or one field. Therefore, the introduction of the damp-like torque and field-like torque based on the measured symmetry of the second harmonic is unjustified. Next, I would like to talk about the method of zero-harmonic. This method is very similar to the method of the second harmonic and therefore has similar problems. This animation shows the experimental setup for this measurement. The sample, for example the bulk indium arsenide, is illuminated by a microwave whose frequency is close to the fMR frequency of the sample, exciting the ferromagnetic resonance in the sample. As a result, there is a magnetization precession in the sample. Additionally, the microwave excites the oscillation of current in this conductive sample. Two electrodes are fabricated at site of the sample, and DC hole voltage is measured. I would like to emphasize this point. The sample is illuminated by microwave, but the DC hole voltage is measured. The hole voltage is proportional to the current and magnetization, which both are modulated. As a result, there are beating between the oscillation of current and magnetization. The second harmonic of hole voltage is measured in second harmonic method, about which I have just explained. This method measured zero harmonic of hole voltage. Therefore, these two measurement methods are very similar. The summing of two frequencies gives the second harmonic. The subtraction of two frequencies gives a zero harmonic. You can read more details about the zero harmonic measurements here in the measurement part and next ref measurement. As you can see, there are many possible configurations for zero harmonic measurement. Both the hole voltage and magnetic resistance may contribute to the measured zero harmonic. The magnetization precession or the ferromagnetic resonance can be excited directly by the microwave radiation, like here, or by electrical current due to the current modulation of magnetization direction. So as you can see, there are many possibilities for this measurement, and therefore there are many contributions. As a result, the interpretation of the zero harmonic measurement is difficult and often ambiguous. I should say that the interpretation of zero harmonic measurement is often even more ambiguous and difficult than the measurement of the second harmonic. The measurement of zero harmonic is known for a very long time. As you can see here, the first measurement of zero harmonic was done about 50 years ago. And the method was named the zero harmonic measurement. However, recently this method was reinvented under a newer and more fancy name. If you are interested to see the content and other parts of this video, you can find the links below this video.